Hi everyone. In today's lecture, we'll be discussing about the step response of parallel LC and series LC circuit. Okay. And we'll also be discussing about the pulse response. So how does the circuit behave when you feed, for example, in a parallel LC circuit, we'll be feeding a pulse of current and see what will be the voltage developed across the tank, the LC circuit. And similarly, we'll also be feeding a pulse voltage for a series LC circuit and try to monitor the current which is actually flowing in the circuit. And also we'll see the voltages across both the capacitors, both across the capacitor and inductor in a series LC circuit. We'll also see the current flowing through both the inductor and capacitor in a parallel LC circuit. So I'll first start with the parallel LC circuit. So in a parallel LC circuit, you have a step current which is being applied, and we are interested in finding out the voltage across the tank or the LC circuit. So first I'll actually try to solve this problem mathematically, and then I'll try to give intuitions as to why those equations make sense. So the impedance of this parallel LC network is SL by 1 plus S square LC, and I'll be using this result omega naught square is the resonant frequency given by 1 by LC. So using that, I can reduce the impedance to be 1 by C S by S square plus omega naught square. Now this, if I multiply with the input which is I naught by S, I will be getting the output which is V naught of S. Now all I need to do is to find the inverse Laplace transform of this, and I have my time domain output voltage for this parallel LC tank. So to find the inverse Laplace transform, I'll just multiply by omega naught and divide by omega naught. So I have I naught by omega naught C into sine omega naught t into u of t. We already discussed the inverse Laplace transform for this is sine in the last class. So this will be your output voltage across the parallel LC tank. Now to find the current through the capacitor, IC of t, it will simply be C dV naught by dt. So IC of t will be the current that is flowing through the capacitor. The direction is in this way. So IC of t is the capacitor current, and IL of t is the inductor current, and II of t is the input current. So here, using this, I'd actually get I naught cos omega naught t into u of t. And to find the inductor current IL of t, I have to simply subtract II of t minus IC of t, because I can just write KCL at this node. I will get this result. So I'd get I naught into 1 minus cos omega naught t into u of t. Now I'll try to plot the inductor currents and the capacitor current and also the voltage across the tank. So the capacitor current starts at I naught. I am just drawing the waveforms now, the mathematical waveforms from the mathematical equations. So it's a cosine signal. And the voltage across the capacitor is, it starts from 0, it's I sine omega naught t. So whenever the current is minimum, the voltage will be peaking. And we know it will be 90 degrees apart. And the peak value of the voltage is peak value of the current divided by omega naught c. 1 by omega naught c is the impedance of the capacitor. So this result again should seem intuitive. And the current that is flowing through the inductor, if I plot it, it's actually I naught into 1 minus cos omega naught t into u of t. Now if you look at this function, cos function, the minimum and maximum value lies between minus and plus 1. So this term will always be greater than 0. It will never be less than 0. And it will go to a maximum of 2 I naught and minimum of 0. So at t equal to 0, the value is 0. And at t equal to pi, that is when cos omega naught t equals pi, or t equals t by 2, where t here is 2 pi by omega naught. That's the time period of this cycle, of this waveform. At t equal to t by 2, that is at this point, when the voltage across the capacitor is 0, you are going to have a current of 2 I naught. At t equal to t by 4, the current through the capacitor or the current through the inductor is I naught, because cos omega naught will be cos omega naught into t by 4 will be pi by 2, cos pi by 2, which is 0. So the function would look something like this. It's a cosine wave just shifted by I naught. So the average value will be I naught. Okay, it's just a cosine wave which is shifted okay. Now this is the mathematical response. We have just drawn the equations. We have just drawn what we got, what we obtained by using Laplace analysis. Now we'll try to explain intuitively why does this waveforms why do these waveforms are intuitively correct. So first, the moment I inject a step current, where it's going from 0 to I naught, the current I naught, because the inductor is going to offer a large impedance at t equal to 0, the current I naught will instantly flow through the capacitor. Okay. Now the moment the current I naught flows through the capacitor voltage is going to increase because it's going to charge the capacitor. So that's what we see here. The capacitor current is I naught in this waveform, the waveform that I've shown here, and the capacitor voltage slowly starts to increase. As the capacitor voltage increases, the inductor will slowly start building current. So IL of t will start increasing. So that's what we see here. There is a very simple and intuitive way of looking at it. We can actually show that mathematically as well. If I find the voltage across the capacitor, if that will be approximately integral of the step, which will be like a ramp at t equal to 0. This is true only at t equal to 0. It will increase like a ramp. And the current through the inductor will be integral of the voltage, voltage across the inductor. So therefore, that will have a parabolic rise. So that's why you see the rise of the through the current will be much slower compared to the rise of the voltage across the capacitor. That's initially. Now, the inductor current, we can see here the inductor current is increasing because the sum of the two currents is always I naught. So the inductor current is increasing and the capacitor current is decreasing. So there will be a point when the capacitor current will become 0 and all the current I naught will start flowing through the inductor. Okay. At that point, the current through the capacitor is 0. Okay. So since the current through the capacitor is 0, that is the point your voltage across the capacitor can no longer increase because it has become 0. It can either remain there, okay, or depending upon the inductor's discharging of the capacitor, it can reduce. So that is the peak value of the voltage that capacitor can store, and that happens at t equal to t by 4. Mathematically we have seen it. Okay, we'll try to compute the energy stored in the tank at t equal to t by 4. So the voltage across the capacitor is maximum, and that is I naught by omega naught c, and the current through the inductor is I naught. So current through the inductor IL is I naught, and this is voltage Vc of t, voltage across the capacitor, which is I naught by omega naught c. So the stored energy in the system at this point, in the inductor it is half L I naught square, and in the capacitor it is half C V naught square, that is I naught upon omega naught c the whole square. And again, using the result, omega naught square equals 1 by LC, we can very easily show this is half L I naught square. So both the inductor energy and the capacitor energy are same, and that's equal to half Li square. So this is the point, both inductor is also storing some energy and capacitor is also storing, and they both are storing equal energies. Now obviously, where does this energy come from? Both energy comes from the current source. The current source had been providing this energy. So I'll just try to compute what is the energy that is transferred from the current source to the LC tank to both the inductor and capacitor by using, by first I'll find the power delivered by the current source and I'll integrate the power. So far only it has, we have come to t by 4 seconds. So 0 till t by 4 p of t dt. Now the power delivered by the current source is simply, the current through the current source is always constant, and the voltage across the current source is nothing but the voltage across the tank. Right now at t equal to t by 4, we have still progressed only till t by 4 seconds, where t by 4 t is 2 pi by omega naught. At that point it has reached a peak value of I naught by omega naught c. So we have to take the product of these two and then find the area under this curve. Okay, so the power curve will be I naught omega naught c, I naught square by omega naught c, and we are supposed to find the area under this. So the voltage is I naught by omega naught c into sine omega naught t. Current is I naught, so it will be I naught square integral 0 to t by 4 dt. So this will be I naught square by omega naught c, and I can write omega 1 by omega naught c as omega naught L. From this result, it's a resonant frequency, so we can write the impedance of both the capacitor and inductor are same. So I can simply replace this as half L, I can simply replace this as L I naught square into omega naught integral 0 to t by 4 sine omega naught t. Now this integral of sine is cosine. You will get by omega naught, and that by omega naught will cancel out with this omega naught. So we will be left with Li omega naught square into cos omega naught t between 0 to t by 4. Actually there is a minus sign. So when you substitute t equal to t by 4, you would get cos pi by 2, which is 0, and when I substitute 0, you will get minus and minus of 1, you will get 1. So the result is Li naught square. So this is the energy that is transferred from the current source, Ei naught, which is transferred from the current source to the LC tank, and that is exactly equal to the energy which we saw here. This term and this term we found by finding half C the voltage square and half L the current square through the inductor and the capacitor and the voltage across the capacitor respectively. And when we added both the energies, that was again equal to Li naught square, and that is entirely delivered by the current source. Now after t equal to t by 4, the voltage across the capacitor, I will just redraw the tank here. So now we have a current I naught, the step current, it's flowing through the inductor right now. Capacitor has developed a peak voltage I naught by omega naught c. Now what will happen here is that the inductor current is already I naught, which is flowing in this direction. Now the capacitor will now again start charging will be now discharged by the inductor. Okay, the inductor will now try to discharge the capacitor voltage, because any EMF across the inductor is going to generate extra current. Okay, so now since this terminal is positive, you are going to increase the current in the inductor. So the inductor current already was, to begin with, it had just grown to be I naught, and the capacitor voltage is also maximum now, so the rate of increase of the inductor current will also be maximum, and it will keep on increasing inductor current till the voltage across the capacitor goes to 0. Okay, so till the voltage across the capacitor goes to 0, so we can very easily compute what is the current that this voltage across the capacitor would have caused to flow across the inductor. Okay, we can very easily compute that as well, and that current, that is the current that is, see, when you actually try to integrate the voltage across the capacitor in the positive half cycle, the inductor was building a current I naught, right? We had I naught by omega naught c, so inductor current is simply 1 by L integral V dt. So the inductor took to build a current I naught, which is nothing when the voltage across the capacitor rose from 0 to a peak value. Now the voltage across the capacitor is now falling from a peak value to 0, but it is always positive, the voltage is still positive. So if I integrate this region, the current is again going to be the same. So therefore the peak current that the inductor will reach is 2 I naught. Okay. Now at this point, at t equal to t by 4 or t equal to t by 2, sorry, this is t by 2, the voltage across the capacitor will come down to 0. All the energy that the capacitor had stored in it is now transferred to the inductor. Okay. Now if you understand here, there is the I naught current from the voltage source is now entirely traveling across the inductor. Now the additional current that is contributed by the capacitor is now further increasing the current through the inductor. Now if I try to compute the energy at t equal to t by 2, this is t by 2, sorry, this is t by 2, the capacitor energy is 0, EC is 0, which is half CV square is 0. The energy stored in the inductor on the other hand is half L 2 I naught square. So that would actually be 2 L I naught square. If you remember, at t equal to t by 4, the energy stored in the inductor was half L I naught square. And I also said the energy stored in the capacitor was half L I naught square. So if this capacitor has now transferred all the energy present in it and converted it into current to the inductor. So ideally the energy should be simply L I naught square, right? But here we are getting 2 L I naught square. So where did the remaining energy come from? That remaining energy comes from the current source. And now because your current source is always constantly equal to 1 I naught. So in this half cycle, the current source, that is at till t by 4, the current source delivered an energy of L I naught square. And similarly in the other half cycle, from t by 4 to 1 quarter cycle, from t by 4 to t by 2, it will again deliver an energy of L I naught square to the LC tank. So the remaining L I naught square actually comes from the current source. So the total energy stored in the inductor is 2 L I naught square. Half L I naught square, initially it already had the initial energy stored in the inductor was half L I naught square at t equal to t by 4. Now capacitor at t equal to t by 2 is going to add half L I naught square, and the current source is delivering L I naught square to it. So totally the energy comes to 2L I naught square. I mean, why am I talking extensively about energy? It will become clear once we go to the analysis of pulse response. You can use a lot of intuitions to find the steady state values. So I thought it's useful to derive it, spend some time on the energy of LC circuits. Okay. Now what happens in the cycle after t by 2? After t by 2, now I will just draw at t by 2. The inductor is now carrying a peak current of 2 I naught. So it has reached a peak value of 2 I naught, and capacitor voltage has now gone to 0. Okay. Now the inductor is carrying current a value 2 I naught. Okay. Out of which I naught flows back to the current source, and the remaining I naught will now charge the capacitor in the opposite direction. Okay. So now that remaining energy is now going to flow through the capacitor, and it's going to charge the capacitor in the opposite direction. And the capacitor is now going to again similarly, initially it had a voltage of I naught by omega naught C. So that is eventually going to go to minus I naught by omega naught C. At that point, inductor only has to lose, and it will come to a value of I naught. The current through the inductor, see, this is the point when since the voltage across the capacitor is negative, inductor will start losing its current. Okay. And when the capacitor voltage goes to its peak negative value, the inductor current will come to I naught. I'll use a similar logic that if the voltage across the inductor is negative, okay, the inductor loses a current of I naught if I integrate it. I said that for the inductor to build a current, we have to integrate 1 quarter cycle of voltage, I naught by omega naught C. If I integrate this 1 by L integral of the voltage, we got that value to be I naught. So same way when the voltage is negative, if I am going to integrate, I am going to get minus I naught, which means the inductor has lost a current of I naught. Okay. And then the capacitor voltage, since it is negative again. Now the capacitor voltage is at its negative peak. Okay. Now the capacitor is now further going to reduce the current in the inductor even more. So in this cycle, capacitor's current will start increasing. Okay. So the capacitor will now start taking current from the current source. Okay. So now I'll also draw the capacitor current. So the capacitor current had a peak value of I naught, and when the voltage reached a peak, it went to 0, and at this point the capacitor current reached a value of 0. Okay. After this, as the voltage across the capacitor goes back to 0, which means you are charging it from a negative value, so which means current is flowing in the forward direction of the capacitor. So all the I naught current will be flowing through the capacitor at t equal to t. So this is back to square one. I mean, we are back to again the initial value. All the current I naught was flowing through the capacitor, and there was no current flowing in the inductor because inductor has lost all its current. In this cycle it has lost I naught. In this cycle it has lost I naught amount of current. Okay. And inductor will come to 0. So at this point inductor current will actually come to 0. So this is one full cycle. So at this point, if you look at it, at t equal to t, capital T, the capacitor voltage is 0 and the inductor voltage is also 0, but the capacitor current is maximum I naught, and the energy stored in the capacitor is 0, and the energy stored in the inductor is also 0. So then where did this energy go? It's a purely lossless circuit. Okay, there are no dissipating elements in the circuit. Then where did the energy go? It then goes actually in the current source itself. Now if you look at the current source delivers always a constant current of I naught. But if you look at the tank voltage, I'll just redraw this waveform, the tank voltage. It was positive till t by 2, and the tank voltage is negative from t by 2 to t. So if you integrate in this cycle, if you see in this cycle from t by 2 to t, the power is actually absorbed by the current source. So therefore that power, when some element is absorbing power, it's going to dissipate energy. So I just showed, if I integrate in this half cycle, we can easily show that the energy that is dissipated in this will be 2L I naught square. All the energy at t equal to t by 2, inductor had all the energy, and that was 2L I naught square. That will be fully dissipated by the current source at t equal to t. So that's what happens in a parallel LC circuit when you feed a step input. And this process continues indefinitely. I mean, for 0, I've done it for 0 to t, the same process repeats. At t equal to t, that is t equal to capital T, after one cycle, both the inductor and capacitor energies become 0. Whatever energy it has gained till t by 2, that was 2L I naught square, is completely lost at t equal to t, at t equals capital T. After that, again the capacitor and inductor will start building energy, and again they will lose energy in the next half cycle, and so on. So that's the way this circuit will progress forever. Okay. So you can give a very similar explanation for a step voltage when you apply for a series LC circuit. So I am going to give a step voltage of 0 to capital V naught, and we are interested in finding the current. Okay, so we can easily show that. I mean, I'll just explain it here. Okay, also let me just take one moment to explain the parallel LC network. So in a parallel LC network, I'll just let me show it here. So the parallel LC network, you had a current flowing through an inductor and a capacitor. So we know the step input, the steady state current is constant. So the DC voltage across the tank should be 0 because the current is not changing. If there is no changing current, then the inductor will carry that current with 0 volts across it. So the steady state voltage has to be 0. The DC value has to be 0. Okay. And but because at the initial transient, when the inductor is actually building its current, the capacitor is also getting charged. So that stored energy in the capacitor is what is responsible for the periodic behavior, that we see in the circuit. This is just a very crude way of explaining it using giving a simple intuitive explanation for it, but we have already done an extensive analysis about how does the energy transfer take place throughout one full resonance cycle. Okay, so similarly I'll come back to this circuit. Of course you can write equations and derive the final results, but I can instantly write the instant you apply a step voltage, the capacitor voltage cannot change instantaneously, so it will behave like a short circuit. The inductor is going to take the entire voltage. Okay, now we also know the steady state voltage across the inductor has to be 0, right? Because it's a DC input, the input is constant, so it has to be 0. So therefore the voltage across the inductor will start from V0 and it will be 0. Steady state value will be 0, but it will keep oscillating between plus V0 and minus V0. Of course, we can show this result very easily mathematically. Okay, by following a similar procedure, you can simply find the Laplace transforms and use Laplace transforms to solve it. Okay, and the voltage across the capacitor on the other hand, because this inductor is going to develop an initial voltage of V0 across it, it's going to build a current. That current is initially going to charge the capacitor. Okay, now the capacitor voltage Vc of t is going to be charged. It's going to start from 0 and it's going to rise. Now until when it will keep rising? It will keep rising till the voltage across the inductor is 0, or as long as the current is flowing into the capacitor, the voltage will keep on rising. Now there will be a point when the capacitor voltage becomes equal to V0, capital V0. The voltage across the inductor is 0. And this is the point when inductor is 0. Until this point, the capacitor has built a voltage of V0. After this, because the inductor now is carrying a lot of current, because the inductor current was also significant. Now at this point inductor current rises here. The inductor current rises from 0 till a peak value, and that peak value again can be very easily shown. It is V0 by omega naught L. Okay, I am not writing the final result, but you can simply take Laplace transforms and very easily show this results. It will be V0 by omega naught L, and also I told you V0 is the peak voltage. You have to multiply it, or you have to divide it by the impedance of the inductor, which is omega naught L. You get the peak value of the current. Now this current is flowing in this direction, so it will charge the capacitor further and it will take the voltage to 2V0. So the voltage across the capacitor will actually go to 2V0. Okay. So at that point the current through the inductor will come to 0. Fine. So we can also explain it this way. The current through the inductor is simply integral of the voltage waveform. So it took t by 4 seconds and 1/4 cycle of a sine wave to get this value of V0 by omega naught L. So similarly, to lose that current, you will have to further go to minus V0 in this quarter cycle. Okay, if the voltage across the inductor is now negative and the voltage across the capacitor will be higher than capital V0, okay, until it reaches 2V0, at that point the inductor current will completely vanish to 0. Now that is the point. The energy stored in the capacitor is half C into 2V0 the whole square. So that will be 2C V0 square, capital V0 square. Again, we can very easily show that half C V0 square is the initial energy stored in the inductor. Okay, the peak energy stored at t equal to t by 4 is half C V0 square across the capacitor here, and similarly the inductor current half Li square, half Li square, which is V0 by omega naught L the whole square, can also be shown to be equal to half C V0 square. So both of them have energy stored in them. and at t equal to t by 2 the capacitor stores an energy of 2 cv0 square, out of which cv0 square comes from the input voltage source. Again, by going in a very similar way as we did for a parallel LC circuit, you can show this result as well. Okay, and the remaining energy half cv0 square is transferred from the inductor into the capacitor, and the capacitor already had at t equal to t by 4 an energy of half cv0 square. From there, from half cv0 square at t equal to t by 2 the total energy rises to 2 cv0 square. Okay, so nearly 3 halves of it gains an energy of 3 halves cv0 square, and that comes from the voltage source and the inductor. Okay, and then the process continues, for one cycle, and the next cycle I already discussed that the capacitor is now going to lose all its energy. Okay, and inductor will gain it. So at the end of one cycle, the current through the inductor will be 0. Same thing happens at t equal to 0 as well, at this point at t equal to capital T, and the same thing happens at t equal to t equal to 0 as well. Both the inductor current is 0, the capacitor voltage is also 0, inductor current is 0, and the capacitor voltage is also 0. The initial energy is 0. So the voltage source transfers an energy of 2 cv0 square in first half cycle, that is till t by 2, and in the remaining half cycle, the second half cycle, it removes an energy of 2 cv0 square. So the net energy transferred at the end of one cycle is 0 from the voltage source. Okay, so that's all about step response for a parallel and series LC circuit. I didn't write the equations explicitly, but it should by now be obvious. The voltage across the inductor is simply V0 cos omega naught t, because it's going to start at V0 at t equal to 0. And the current in this circuit, we can very easily show the current in this circuit is again V0 upon omega naught L sin omega naught t. So I just found the peak voltage divided by the impedance of the inductor. Okay, that is going to be the current that is flowing in the circuit. I mean, you can simply differentiate V0 cos omega naught t, and I mean you can use I equals C dVc by dt. Okay, or you can simply integrate this result. You would get this equation. 1 by L integral V dt will give you the current through the inductor. This is the inductor, which is also same as the capacitor current. If I substitute omega naught L as 1 by omega naught C, I will get omega naught C into V naught into sin omega naught t. So that will be the capacitor current, and you can write the capacitor voltage as the input voltage minus the inductor voltage. So that will come out to be 1 minus cos omega naught t into V naught into u of t. So this will be the voltage across the capacitor. Okay, this is the inductor voltage, and we have also find the series current. So this finishes the step response of a parallel LC circuit. So now we will see how does this parallel LC circuit behave when I apply a pulse input. Okay, I am going to call it as T0, the width of the pulse, and amplitude, it can be either current or voltage. It can, for a parallel LC we will assume a current pulse, and for a series LC it will be a voltage pulse. So first I will use, now that we have analyzed the energies extensively, I will use intuitions to solve this problem. So for first I will assume the pulse width is actually t, where t is the resonant time period, which is t is 2 pi by omega naught, which is t naught, capital T naught is equal to t. So it's an I naught, and it exists for 0 till t. Now what happens to the circuit the instant you apply a step input? We saw that the current was building up in the capacitor, and the current across the capacitor was going from 0 and coming back to 0 at t equal to t. coming back to I naught at t equal to t, and the voltage across the tank was again okay, and we also saw the current through the inductor. The current through the inductor for this circuit would reach a peak and go back to 0. So this is the inductor current and this is the capacitor voltage or the tank voltage. Now the peak value of the inductor current we showed was 2 I naught, and the peak value of the tank voltage was I naught upon omega naught C, okay, I naught into Z, the impedance of the capacitor or the capacitor, and which will also be equal to the impedance of the inductor. Now from this result we can see that we are applying a pulse of input in time. I am applying a current pulse. So this circuit is going to behave exactly the same way like a step input, but what we are doing at t equal to 0 or t equal to t is that we are making the current to go to 0 immediately. That's what it's a pulse input. So it exists only for t seconds. Now at t equal to t, the energy stored in the capacitor is 0 because the voltage across the capacitor is 0. The energy stored in the inductor is also 0 because the current through that is also 0. And again, I already discussed what happened. The first half cycle you delivered an energy of 2L I naught square. You can just go back a few minutes and see that we derived all these results. In the second cycle, in the second half of the cycle, we dissipated energy of 2L I naught square. The current source dissipated or absorbed the energy of 2 I naught square. So eventually at t equal to t, the energy of this system came to 0. At that point, I am suddenly making the current to go to 0. The instant you make that, the capacitor current will instantly come to 0. I'll just draw it in red what happens to the final values. The capacitor current will instantly come to 0. Since the capacitor current comes to 0, there is no current to charge the capacitor anymore. So the capacitor voltage will stay at 0. Since the capacitor voltage is 0, there is no EMF across the inductor, and inductor will no longer build any voltage, any current. So that will also stay at 0. So therefore, the system will stay at a 0 energy state forever. Meaning both the inductor voltage will be 0, inductor current will be 0, capacitor current will also, capacitor current will instantly go to 0. It's a capacitor, its current can change instantaneously, but voltage cannot. So the whole system will come to a halt and everything will be 0. There will be no energy stored in the system. So using this energy I could very easily show this. Okay. Now if you are to solve this problem mathematically, how would you solve it? So what I will do is, it's a pulse input. I am applying a current from 0 to I naught till t seconds. So I will split this as a step, positive step at t equal to 0, and I am also going to apply a negative step at t equal to t. At t equal to t, I am going to apply a negative step of value minus I naught. Now if I add these two out inputs, I am going to get the step, the input. I mean, when I add these two, this and this input and this input, I will get the pulse input. So by using superposition, I am going to find what will be the final values. So if I apply a positive current, for example, the voltage of the current through the capacitor IC of t is simply I naught cos omega naught t. If I apply a step input, we just showed that equation in the beginning of the lecture. Now if I apply a negative current, it's simply going to be minus I naught. So it's going to be IC of t minus t, that is after t minus t. It's going to be minus I naught because it's a negative step into cos of omega naught into t minus t into u of t. Now it's a periodic signal where t is 2 pi by omega naught t, omega naught. So this is nothing but omega naught into t minus t is again cos omega naught itself. So you will get minus I naught cos omega naught t into u of t. So the total current is sum of the two currents. Okay, the total current, I'll write ICT as the total current, will be IC of t because of the first step input plus IC of t minus t because of the step input that's applied after t equal to t seconds. the sum of the two will be 0. So this is mathematically you can show it, and similarly you can show this for every result. All the sinusoids will be same because you are just shifting it only by t seconds. Okay, all the solutions will be same. You are just adding, you are just putting a negative sign to the current, so they'll all add up to 0 after t equal to t. Before that it will behave like how the input was for a simple step input. Okay, so using the energy I could very easily solve this. I didn't have to go through the math at all. But now similarly we will try to solve for a different pulse width. What if the pulse width is 0 till t by 2? I naught, the width of the pulse is t by 2. We saw for this waveform, I'll just draw the overall for the parallel LC tank. So the current input is actually a pulse of value t by 2. It exists for t by 2 seconds. Now again the same process continues. First the capacitor current will be a peak and the voltage across the capacitor will start building. At t equal to t by 4, the voltage across the capacitor will be maximum. At t equal to t by 2, the voltage across the capacitor will come to 0. And the current through the inductor, we said, will increase and it will reach a value of I naught at t equal to t by 4, and at t equal to t by 2 it will reach a value of 2 I naught. Okay. Now what we are going to do is that the inductor is carrying a current I naught and peak current of I naught, and capacitor, this is the capacitor voltage, so I am going to write I naught by omega naught C. Okay. The capacitor current will be different. The capacitor current will start from a peak value of I naught and then go to 0 here. Okay, and it will also go to a negative minus I naught at this point. So but we have already done this, so I will just go back. Now at this instant we are making the input go to 0. Okay, the instant we are going to make the input go to 0, what's happening is that the inductor now has a current of 2 I naught flowing through it, and the capacitor has 0 volts across it. Now this is a very simple problem. It's a simple parallel LC circuit with an initial condition of 2 I naught. So obviously we can simply argue that from this cycle onward it will just behave like a circuit, a sinusoid. So the inductor current will go from plus 2 I naught to minus 2 I naught, and the inductor voltage, the capacitor voltage or the voltage across the capacitor will actually go from, it will be a sinusoid, it will rise to a peak value, and the peak value will be 2 I naught by omega naught C, and then it will keep going back and forth between positive and negative values. So this will be the, and this we already know. If you know the initial energy stored in the inductor, you can easily compute what will be the steady state value. Now the input is 0. After this, input no longer exists, so I can ignore the input and analyze this like a simple parallel LC circuit. So the peak value of the current is going to be 2 I naught, and the peak value of the voltage across the tank or the capacitor is going to be 2 I naught by omega naught C. So you can also compute the peak energy stored in the capacitor. That will be half C 2 I naught by omega naught C the whole square. Okay, if I substitute omega naught C, use the result omega naught square equals 1 by LC, this result simply reduces to 2L I naught square, and that was the energy stored in the inductor at t equal to t by 2. So it is half L into 2 I naught square, which is 2L I naught square. So that energy stored in the inductor will keep going to the capacitor, and it will keep shuffling between the capacitor and inductor indefinitely. So the peak value will be 2 I naught. So if I leave the circuit at t equal to t by 2, I will get this. And again we can very easily show the inductor current. I can just split the using mathematics. I'm just going to show this result, the same result. The voltage across the current pulse can be assumed as a superposition of two current pulses, one starting at 0 and another one with a negative sign starting at t by 2, and this is minus I naught. So when I apply the positive current pulse, the current through the inductor is going to be I naught into 1 minus cos omega naught t into u of t. For the negative pulse, it's going to be I naught with minus I naught into 1 minus cos of omega naught t minus t by 2 into u of t minus t by 2. So I am now going to draw this waveform for t greater than t by 2. So this result, cos of omega naught t minus t by 2 is simply minus cos of omega naught t. Okay, so this result is simply going to be minus cos omega naught t. So this I am going to draw this after t greater than t by 2. So in the after this, these two I naught and I naught will be cancelled out. This term and this term will cancel out. For t greater than t by 2, the first term will anyways remain the same. The second term, on the other hand, you are going to get minus cos omega naught t into I naught plus cos I naught into cos omega naught t minus t by 2. This will simply be, this is minus cos omega naught, so you will actually get minus 2 I naught cos omega naught t. So you can see here the current actually doubles. So which is what we actually predicted. We actually predicted the waveform to have twice the current value after that. Okay, so this is the value in the steady state. Okay. Now we will analyze for the case when the pulse width is actually t by 4. So this is I naught and it's t by 4. So when you apply a pulse width of t by 4 for a parallel LC circuit, a current pulse of width t by 4, what happens is that the voltage across the capacitor will slowly build to a peak value of I naught upon omega naught c. This is t by 4. The voltage across the inductor, the current through the inductor will grow to a value of I naught. Okay. At this point, I am going to suddenly make the input go to 0. So now it reduces to a circuit like this. You have an inductor carrying a current of I naught in this direction, and you have a capacitor having a peak voltage of I naught by omega naught c. So you can also, we have already shown the energy stored in the inductor was also half L I naught square. If you find this half, use half CV naught square, we can show it is half L I naught square. And the energy stored in the inductor is half L I naught square. Now what happens the instant you are going to drop it at this point? Now we know what would happen is that the current through the inductor will now start discharging the capacitor. It's going to charge it in the opposite direction. Okay, and the current through the inductor will go to 0, and again it will again further the current through the inductor will go to 0. Okay, I mean after some time, as long as the voltage across the capacitor is positive, the current through the inductor is going to build to a peak value, and it will keep on building till the capacitor voltage goes to 0. Now what will be the peak value of the current? How do we find that? That I can very easily use energy conservation, because there is no loss in the system. Okay, so the initial energy across the inductor is half L I naught square. I am going to, at this point when the inductor current is at peak, the capacitor voltage will be 0. So using that, I can say energy across the capacitor is 0. All the energy stored in the capacitor has been fully transferred to the inductor. So I'll just equate the two energies. So the inductor energy is going to be, the final inductor energy is going to be half L. I'm going to call the final current, the peak current, as I peak. is going to be half L I peak square. That will be equal to half L I naught square, which is the initial energy stored in the inductor, plus the energy transferred from the capacitor, which is half L I naught square. We already showed it's, if you use I naught by omega naught c, you can show that the energy stored in the capacitor initially is half L I naught square. So this will be L I naught square. From this, your I peak will be root 2 times I naught. So the peak current that it will go will be root 2 times I naught. Okay, previously it used to go to 2 I naught when there was a current source, but now the pulse, it's a current pulse, so it had gone to 0 at t equal to t by 4. So the peak current it will go to is root 2 I naught. Okay, so from that we can again show that the peak voltage after that, which it will be going to, will be root 2 I naught by omega naught c. Okay, that can be very easily shown. Okay, so I need to get the same energy, when the current through the capacitor, voltage across the capacitor is peak, the energy across the inductor has to be 0. Okay, so again that result will come through this half c v naught square. That will again come out to be L I naught square. Okay, you can show that if I use root 2 I naught, you will get L I naught square, which is same as the peak energy stored in the inductor. So by using energy conservation, I could very easily show this results. Okay, so which is why I did all the energy analysis for the in the beginning part of the lecture. Again, you can show this result very easily mathematically. So you are going to have I naught. I'll just use the superposition of two step inputs. So I naught into 1 minus cos omega naught t is into u of t is going to be the step input at t equal to 0, minus I naught into 1 minus cos of omega naught t minus t by 4 into u of t. So now if I try to draw this for t greater than t by 4, see u of this is u of t minus t by 4. So for t minus t by 4, this result u of t and u of t minus 4 are same. So the first term will I naught and I naught will cancel out. So you will be left with I naught minus I naught cos omega naught t plus I naught cos of omega naught t minus pi by 2. So that will be sine omega naught t. So you'll actually get I naught into sine omega naught t minus cos omega naught t. So this very easily you can show, it will reduce to root 2 I naught into sine of omega naught t minus pi by 4. Okay, or we can also show this as minus cos omega naught, but I mean it's a pure sinusoid with 0 average value. That's all I wanted to say here. The peak value here is root 2 I naught. I can show this by multiplying and dividing by root 2. Okay, you can reduce this, you can just add two sinusoids, you would get this expression. Okay, so we could easily find that result using mathematics, but we could find the same result easily using energy conservation. So that's all there is to this problem. So for different pulse widths, we can actually find what will be the final state or what will be the peak current values in the steady state by using energy conservation. It's extremely simple that way. Okay, so I'll stop at this point. In the next lecture, we'll discuss what will happen if I feed periodic inputs to parallel LC tanks. So that will be the discussion for the next lecture.